Hey guys, how's it going? All right, so let's get started here. All right, guys, this is the last topic in the polynomial functions unit. It's called equations and graphs of polynomial functions. All right, so for example 1, it says multiplicity of a 0, and then consider the degree 3 polynomial functions below. So first of all, this guy's going to be a degree 3 polynomial because when I expand this x minus 2 cubed, the highest power will be x minus 2 cubed. Now what you're going to see over here is that this guy hits the value of 2, so the 0 of the function is going to be x equals 2 will be the 0, and then it comes through, okay? Now, we have a special name for this. This guy over here is what we call a point of inflection. So what we mean by that, you may have discovered concavity a bit in your physics courses when you're talking about mirrors and stuff like that. But the concavity of this guy over here, from here to here, this is a concave down curve that's increasing, and now it switches to a concave up curve. So point of inflection is when it switches from either concave down to concave up or vice versa, okay? So for this guy, which has a multiplicity of 3, we have a point of inflection at this guy. Now, moving on to example B, in this case, we have two zeros. We have a 0 at -1, and we have a 0 at 2. Now, what's different over here is that if you look at so when we say multiplicity, we're talking about the exponents associated with each factor, okay? Now, in this case, we have an exponent of 1 and an exponent of 2. That means the x plus 1, so the 0 of x equals -1, has a multiplicity of 1. The 0 of x equals 2 has a multiplicity of 2. Now, what we know is different here. So for the x plus 1, we're looking at this 0 here. The graph, it passes straight through. So it passes through. Now, so does the other one in the previous example, but so this one passes through. This one passes through as well, but it passes through with a point of inflection. Well, this guy, there's no point of inflection. It just passes straight through. Now, for this 0, the graph comes down. It touches the x-axis at x equals 2, but then it bounces back up. So for here, we say that the graph is tangent to the curve, okay? Now, what you notice here, so if the multiplicity was 3, we have a point of inflection. If the multiplicity is 1, it passes straight through the graph. When the multiplicity is 2, the graph is tangent, okay? Look at the third example. Again, this is a degree 3 polynomial, so when I expand it, I will have an x cubed. But the multiplicity of each factor is 1. So at the root of -2, it passes straight through. At the 0 of -1, it passes straight through. And at the root of +2, it passes straight through as well. So for all three of these, the graph passes through. So we need to understand these properties when we're examining the graphs of other polynomial functions. Okay, so for example 2, determine the equation of the polynomial function given by each graph. Assume the least possible degree. Okay, I'll explain what this part means in a second. So we're going to start and we're going to write out what are all of our factors going to be. So we're going to write this out in factored form. So this one's going to look like y equals x plus 2. The middle term is x. That's this guy over here. And this guy is going to be x minus 2. Okay. Now, knowing what we know about the multiplicities. So what we said in the previous example, if the graph is tangent, that means it has a multiplicity of 2. If the graph passes straight through, it has a multiplicity of 1. So the exponent on this term here is going to be 1. And then if the graph has a point of inflection, like it does here, it changes from concave up to concave down, it's going to have a multiplicity of 3. Okay, perfect. So we're so far. Now, what we don't know right now is what the leading coefficient here is going to be. So we're going to put in an a value for leading coefficient, and we need to be able to solve for what this a value actually is. To do that, we're going to use this point right here. So So anytime that a graph passes through a point, like it does here at 127, we're going to use this as x and y and plug it into our equation, and then we're going to solve for a. So in this case, our y value is 27. We don't know a yet. We have 1 plus 2 squared times 1 times 1 minus 2 cubed. So we have 27 equals a. 1 plus 2 is 3. Squared is 9. 1 minus 2 cubed is negative 1. So we have 27 equals negative 9a. Therefore, a equals negative 3. So our equation is going to be, I'm just going to write this here, y equals negative 3, x plus 2 squared times x minus 2 cubed. Okay? All right. For the second one, similar process. We're going to start. Don't know what the leading coefficient is, so I'll leave that as an a. We have x plus 4. So if the x-intercept is negative 4, that means the corresponding factor is going to be x plus 4. And we have a multiplicity of 1. Our next 0 is negative 1. So that means we have x plus 1. The graph is going from concave up. It switches to concave down. So this is going to be a point of inflection. So that means we have a multiplicity of 3. Similarly, over here, we have another point of inflection. And so the factor there is going to be x minus 4 cubed. Okay. Similar to what we do, we're going to take this point 0, negative 16, plug it in as your x and y. So we had 0 plus 4, 0 plus 1 cubed, and 0 minus 4 cubed. So we get negative 16 equals a times 4. 0 plus 1 cubed is 1. Negative 4 cubed is negative 64. Okay, so now we get negative 16. 4 times negative 64 is negative 256a. Divide both sides by negative 256. And on your calculator, you can just do this and go math frac, but you're going to get a equals 1/16. So our answer to this guy is 1/16 x plus 4, x plus 1 cubed, x minus 4 cubed. Okay, that's going to be the answer for this guy over here. Okay. Example 3. For the function, determine the y-intercept. So we're going to have, so for y-intercepts, we want to make x equal to 0. And that will give us our y-intercept here. So we're going to go y equals negative 2, 0 minus 3 squared, 0 plus 1, 0 minus 1 cubed. So equals negative 2. 0 minus 3 squared is 9 times 1 times negative 1. So this is going to be a negative 1 here. So negative 2 times 9 is negative 18 times negative 1 equals positive 18. That means 0, 18. So this is 12, 14, 16, 18 will be right here. Our x-intercepts, we have an intercept at x equals 3. So 3 minus 3 will make this guy equal to 0. So we have one here. We have one at negative 1. We have one at positive 1. Okay. What are the end behaviors? Now, what we want to remember from earlier on in this unit is we had 3 graphs that we had to have memorized. Sorry, 4 graphs. So this was y equals x squared, y equals negative x squared, y equals x cubed, and y equals negative x cubed. Okay. Now what we have here, what is the degree? Well, we have an x minus 3 squared. and x plus 1 to the 1, and x minus 1 cubed. So if we add up these three multiplicities, 2 plus 1 plus 3, we get 6. Okay, so the total degree of this function is going to be 6. Now 6 is even with a negative leading coefficient. That means it's going to behave like this one over here. So we say like this one over here, it has a negative left end behavior and a negative right end behavior. Okay, so this is going to help us when we're sketching the graph. Okay, we know it starts negative over here and it's going to finish negative over here. Okay, so looking at this, we start over here. Now what's the graph doing at this 0 here? Well, at this 0 we have a multiplicity of 1. That means the graph is going to be passing straight through. Now we know where the y-intercept is. Okay, now so to hit over here, we're going to come back down towards this one. At this intercept of x equals 1, it's going to be corresponding with this factor here. We have a multiplicity of 3. Now multiplicity of 3 means this graph is going to have a point of inflection. So it's going to go down like this, and now it's going to come back up. And at x equals positive 3, it's corresponding to this one over here. We have a multiplicity of 2, which means the graph is tangent to the curve. So it's going to look something like this. Okay. Now, when we say sketch, we really do not know how high this maximum point is here or how low this minimum point is over here. Next semester in calculus, we'll show you how to figure out how high this graph gets here and how low this graph gets over here as well. Okay, so we're going to be able to figure that out. The last bullet says, over which intervals is the function positive and negative? Okay, so I'm going to say, so where's a positive? It's going to be from here to here. The graph is positive, and that's really it. Okay, so f is positive on negative 1 to 1. Here's your interval over here. Okay, now figuring out where is this function going to be negative is from here to here and then from here. So f of x is negative on 1 to 3 unioned with 3 to infinity. Now, why am I not including 3 here? Well, the function is equal to 0 at x equals 3, and 0 is neither positive or negative, so we're not going to include it in these intervals over here. So from 1 to 3, it's negative, and then from 3 to infinity again. Okay, example 4. So we're switching over here. Instead of dealing with polynomial functions, we're dealing with polynomial equations. Okay, so in the previous examples, we had like, it was always y equals, and then a graph like this. But now the question is saying solve the equation. And what solve the polynomial equation means, it means figure out what this screen is so sensitive right now. Every time I touch the wrong part of it, it switches to the next page. What x equals. Okay, so that's what solve the polynomials equation is going to mean. So in this case, it's nice because this guy's already in factored form. So all the work's already been done for us in this question. So I'm just going to say what makes what values of x will make this guy equal to 0. Well, if I put in a 3 here, or a negative 2, or a positive 4. So x equals 3, negative 2, 4. Done. Okay, so it's in factored form. We just pick these guys off. For this example over here, this polynomial is an expanded form, so we need to be able to factor this guy first, and then once it's factored, pick off the roots to the equation, just like we do here. So what are our potential integral zeros? Are going to be plus or minus 1. So this is the stuff that we did in the previous section in the factor theorem. And we're going to start testing these values. Okay, guys, I'm just going to do this on my calculator over here to figure out which one works. So a -2 works. So this work is p of -2 equals 0. Therefore, x plus 2 is a factor. So we're going to get -2. I use my synthetic division now to figure out what the other factor is going to be. So we get x plus 2, x squared plus x minus 12 equals 0. And then this guy over here factors nicely for us into x plus 4, x minus 3. So we get -2, -4, and 3 are going to be the three zeros or the three roots to this equation over here. Okay, so sorry, the word guys over here, these are the three roots to the equation, not the zeros. So these are the roots to the equations over here, is what we call them. Sound good? Okay, so similar idea for this guy over here. Our potential integral zeros are plus or minus 1, 2, plus or minus 3, or plus or minus 6. I'm just going to do this on my calculator here, guys. I'm just going to start plugging in values until one of them works. Three works, so p of 3 equals 0. Therefore, x minus 3 is a factor. Okay, so we're going to use our synthetic division, figure out what the other corresponding factor is going to be here. If you need a review on this stuff, guys, go and check out the video on the remainder theorem section there. We have made a couple videos on that stuff, one of them specifically on long division and synthetic division. All right, so here's what we're left with. So we have x minus 3, and then we have x squared minus 4x minus 2. Now, the problem you might recognize with this question is this guy over here is it's not factorable. Okay. Now, just because the quadratic over here is not factorable does not mean it's not solvable. So therefore, we want to use the quadratic formula. So we did the quadratic formula quite a bit in Math 20. Hopefully it's very familiar. Guys, on the previous slide, I had the quadratic formula for you. All right, so here's our quadratic formula. So based off this, our a equals 1, b equals -4, and c equals -2. Okay, so x equals we need to remember, how do we simplify this guy properly? Root 24 equals 4 times 6, root 4 times 6. Square root of 4 is 2 root 6. So x equals 4 plus or minus 2 root 6 over 2. 4 divided by 2 and 2 divided by 2 works. So we get 2 plus or minus root 6 as our other two roots. So our three solutions here are x1 equals 3, x2 equals 2 plus root 6, and then x3 equals 2 minus root 6. Okay. All right, so there's our three solutions, guys. Like that, a little bit more difficult when you have to use quadratic formula, okay? But definitely try a few one of these ones for practice like that and make sure that you're getting kind of good and practiced up on how to do these types. All right, so over here, we want to be able to give a complete graphical solution to the nearest 10th. Now, what we mean by complete graphical solution, this is what I'm talking about. If this was ever like a written response question on a test, and these are kind of the standards that we kind of expect. One for a complete graphical solution is going to be you need to state your window settings. Okay. We want you to sketch what you see on your calc. 3, we want you to label your functions. 4, and this is most important, make sure you actually state your solution. Okay, so this is the work that we need to be able to see for a complete graphical solution. So before I get started here, I think it's going to be easier. I'm just going to modify this equation a bit, and I'm just going to do this by setting one side equal to 0. So I'm going to subtract 2x cubed from both sides. I get this. Subtract 6x squared from both sides. And we get this. Subtract x from both sides. And we get this. And subtract 6. And we're left with this. Okay. Sorry, guys. My other graphing program is not really working great on my calculator emulator. So I'm just going to do this on my calculator, which you can't see right now. So we're going to go y equals x cubed minus 11x squared plus 3x minus 7. I'm going to press graph. And what I see here is I'm not seeing a great picture. So I'm just going to modify my window settings here. And I'm seeing something like this. Okay, so it looks like the graph's coming up over here. It would be coming down over here, but I don't really see that. It's really what I'm looking for is I'm looking for this x-intercept right over here, right? So if I kind of put this over here, second calc 0, and figure out what this guy's going to be here. We're asking this one for the nearest 10th. This point is 10.8, comma 0. So the work we need to show here is our window settings. Our window settings are going to be, the ones I used, are from negative 10 to 20, scale of 1, and the same things for my y was actually negative 20 to 10, scale of 1. So there's my window settings here. We've sketched what we see. We need to label your functions. So we're graphing y equals 0 for this guy here. And the second one is going to be y equals x cubed minus 11x squared plus 3x minus 7. Okay, we've labeled our functions. We sketch what you see on your calculator. Last, we need to state our solution. My solution is x equals 10.8. We're rounded to the nearest tenth, like this. So that's going to be our solution there. All right, guys. So this is it for topic 3.4, which is called equations and graphs of polynomial functions. And this is the last thing that we're going to do for chapter 3 here, guys. As always, guys, just let me know if you have any more questions of that. Send me a message or talk to me in class, and I will see you in the next video. Talk soon.